Hello, my dear friends. Welcome to my channel, Study with me. Hope you are doing well. And from today, we are going to discuss the chemistry optional for UPSC Civil Service examination. And in this video, we are going to discuss the paper 2 topic, that is pericyclic reaction. So, the most organic reactions, both in the laboratory and in living organisms, are polar reactions or radical reactions. However, there is a third class of reaction for which neither an ionic mechanism nor a free radical mechanism can be proposed. For these reactions, which are extraordinarily insensitive to catalysis, acid and base are largely without effect, and even the presence of solvent seems of little relevance because of the reactions proceeds as well in the gas phase as in solution. These reactions were frustratingly difficult for chemists to understand for many years because of the formation of an intermediate could not be speculated. In such reactions, which were once referred to as no mechanism reactions. So, this which will also referred to as no mechanism reactions, starting materials and products are separated by a single transition state. It is a surprise to understand that some of these reactions can even be degenerate reactions eligible to be called no mechanism, no reaction reactions, in which the starting materials simply rearrange to themselves. So, what are pericyclic reactions? Pericyclic reactions are concerted reactions that have a cyclic transition state. In these reactions, electrons in one reactant or more are reorganized in a cyclic manner. A concerted reaction is a single step reaction in which a reactant is converted into the product without the intervention of an intermediate. Here, bond breaking and bond making occurs synchronously, though not necessarily symmetrically. And there will be an influence of thermal and photochemical conditions on pericyclic reaction. That is, the activation energy for the single transition state of a concerted pericyclic reaction may be provided by heat, that is the thermal induction, or by ultraviolet, that is the photochemical induction. Some pericyclic reaction proceeds only thermally while certain others proceed only photochemically. However, some of them occurs under both thermal and photochemical conditions. The most remarkable observation about such reaction is that thermal and photochemical processes yield products with a different stereochemistry. So, the thermal and photochemical process will have different products that will differ in stereochemistry, and this can be said that there is an allowed and forbidden reactions. That is, it is customary to categorize pericyclic reactions as allowed or forbidden with reference to the energies of concerned cyclic transition states and the relative ease with which the reaction takes place. If under the condition chosen a reaction has a low energy transition state, it becomes allowed. If it has a very high energy transition state, it becomes forbidden. Okay. Now, we will consider about the Woodward-Hoffmann theory of pericyclic reactions. This is an important one in the aspect of UPSC. So, the theory of conservation of molecular orbital symmetry is introduced by them. According to the principle of conservation of molecular orbital symmetry, during the course of a pericyclic reaction, the molecular orbital symmetry is conserved. This means that the MOS of the reactant must flow smoothly into the MOS of the products without any drastic change in symmetry. MOS means the molecular orbitals. Okay, so we can say that in other words, molecular orbitals in the reactant get transformed into those orbitals in the product, which possess the same symmetric properties with respect to the elements of symmetry preserved in the reaction. Only in such a case will the bonding intercation help stabilize the cyclic transition state. Otherwise, the activation energy would be much higher and the concerted cyclic reaction cannot occur. So, in this, we will have an approach called FM approach, that is Frondia molecular approach. So, the Woodward-Hoffmann rules will be introduced to the FMO approach to predict the symmetry allowed and symmetry forbidden processes. So we will consider the FMO approach here. There are many approaches that Woodward and Hoffman introduced to predict this. One of them is Huckel-Mobius system. In our UPSC aspect, FMO approach is the most important one. So we will consider the FMO approach here. In the case of FMO approach, there are some rules. These rules are based on an analysis of molecular orbitals of reactant and product of the concerned concerted reaction, which is simplified by the application of the Fondier molecular orbital theory. And in this, we consider only two molecular orbitals called Fondier molecular orbitals of the reactants. These Fondier molecular orbitals are the highest occupied molecular orbitals, that is called a HOMO. HOMO is the name of a highest occupied molecular orbital, and the other one that will be considered as the molecular orbital is the lowest unoccupied molecular orbital, that is called LUMO. So the terms highest and lowest refer to the energy of the orbital, and the terms occupied and unoccupied refers to whether the orbital is populated with electrons or empty. So once the FMOs are identified, it becomes possible to predict a reaction geometry and subsequently to decide if the predicted geometry for the concerned reaction is symmetry allowed or symmetry forbidden. So now we can study about the FMO approach. So for studying FMO approach, we have to know about the MOs, that is molecular orbitals. So there is a simple trick for studying the MOs. First, we will study about the C4 system and then C6 system, and after that we will go to C3 system and then C5 system. So first, C4 system. The C4 system is buta 1,3 diene, that is CH2 double bond CH, CH double bond CH2. So it is a C4 system. It can be represented as this. This is the C4 system. Now we have to draw the molecular orbitals of buta 1,3 diene. So the trick is, firstly draw a line, that is the energy line. It is a C4 system, so just draw 4 lines here like this. Here is the 4 lines. Then add 4 electrons. This is the representation of the electrons for each of the line. Okay. Then we have to draw the positive side and the negative side for these all MOs. So before that, the first 2 lines, it is a C4 system, so it has a bonding and anti-bonding. I think all of you will be knowing about the bonding and anti-bonding. What is that and about this? So the bonding will be the first 2 molecular orbitals. This will be the bonding and this will be the anti-bonding. So now we have to fill it with positive and negatives. For that, I will give you a trick. The first part, first line, the bottom line will have all positive signs on the upper side. Here like this, and then this side of the positive side, what will be this side in negative side, and the other side of the positive sign will be always the negative one. So we will put the negative side to the other side. And for the second line from the bottom, the first one will have positive sign, and the trick is that the last one always will be the negative sign. So the first one will be positive and the last one will be negative. And for the bonding, this I already said that this is a bonding, so it will have only one node. Here is the node, number of node will be what will be the number of nodes? The first line, bottom line will not have any node, that is 0, and the second line will have one node, and the third line will have two nodes, and the fourth line will have three nodes, and for C6 system this will increase. Okay, so the number of nodes will increase. How an node will be drawn? The node is that if it has a positive and negative sign, the node will have when there is an opposite sign to the same side. If it has a positive and this one have a negative sign, then here will be a node. This is called a node. So we already know that what this line have one node. So the one node can be only introduced here. So here there is no node. So if it is a positive one, then what will be this one? This will be a positive one. And if it is a negative one, what will be this? This will be negative. So the node will be introduced here. And what will be the next one? Okay, I will say one thing, that the first one will be in the third line, 1 2 3, third line, the first one will be positive sign and the last one will be also positive sign. So don't please remember this. The first one will have all positive sign, the second one will have the first positive and the last negative, and third one will have positive in the first and positive in the last. And here we know that there is a two nodes here. So where can be the two nodes can be introduced? Here and here we can introduce two nodes. How? If this will become a negative sign, then this here will be a node can be introduced. And if it is a negative sign, here will not have a node, and also here can be a node introduced. So in the next, the fourth line, the first one will be positive and the last one will be negative. And we know that here three node will be introduced, 1 2 and 3. So this will have an alternative positive and negative sign. So we can introduce three nodes here. So in this we know that we can conclude by this that the first one will be always positive. First line will be always positive, and the second one will be positive in the first and negative in the last. And the third one will have positive in the first and positive in the last. And the fourth one will have the alternate positive, negative, positive, negative. This is the trick for drawing the positive and negative signs and nodes. Okay, I think you get the idea of putting positive sign and negative sign in the MOS. Next, we have to introduce electrons to this MOS. So this is a C4 system, and this will have 4 electrons in it. So this is the first MO, this is second, third and fourth. So it has 4 electrons. The first MO will definitely have 2 electrons in it, and the next one also have 2 electrons. Then the 4 electrons are given to here. So we do not have any electrons to fill these orbitals. So this will be the HOMO for ground state. This is a ground state. This will be the HOMO. How HOMO is the, I have already said that HOMO is the highest occupied molecular orbital. So this is the highest occupied molecular orbital. The occupied means the electron occupation. So here the electrons are completed in the second one. So this will be the HOMO, and the LUMO, that is the lowest unoccupied molecular orbital, will be the third one, isn't it? So this will be the LUMO. And we consider ground state for thermal and excited state for photochemical. I will take a class about that. So just remember that ground state will be for thermal and excited state for photochemical. Okay. So now we have to fill electrons in the excited state. The first one will have 2 electrons. The second one will have only 1 electron, because if it has 2 electrons, the second one will excited to the third MO. So the third will have an electron, fourth will not have an electron. So this electron is excited to the third one, that is the excited state. So here what will be the HOMO? The HOMO will be the third one, isn't it? HOMO, highest occupied molecular orbital, will be the third one. And what will be the LUMO? LUMO will be this one, fourth one, isn't it? This will not have any electrons, so this will be the LUMO for this C4 system. Okay, now we will study about the C6 system. This will have molecular orbitals of hexa 135 triene, that is CH2 double bond, CH single bond, CH double bond, CH single bond, CH double bond, CH2. This is the C6 system. So we already know about drawing the energy of molecular orbitals. Draw a line like this for energy, and this is a C6 system, so we have to draw 6 lines here. 1, 2, 3, 4, 5 and 6. Okay, now we have to put 6 molecular orbitals here. Okay, 1, 2, 3, 4, 5, 6. Okay, I have drawn. So now we have to complete this by adding positive and negative side. So firstly we have to know the nodes of all these MOs. Nodes. The first one will have 0 nodes, and the second one will have 1 node, then 2, 3, 4 and 5 nodes. And I have already said that the first one will have all positive signs in the upper side, so this will be all positive, and the second one will have first one positive and last one negative, and only 1 node. So we can draw the node in the middle of this 6. So 3 1 here and 3 will be here. So these 3 will have positive sign. So here no node, and these 3 will have negative sign. So the node will be in the middle of this. And if we have the third molecular orbital, in this the first one will be positive sign and the last one will be also positive sign. I have already said in the C4 system. So this will have positive and this will have also positive, and we have 2 nodes. So we can these 2 nodes be considered introduced. So we can distribute these 2 nodes by cutting this by 2 and 2 and 2. So this will be cut by 2 and 2 and 2. So this first one will have the same sign. So in the middle of them will not have any node. So the first 2 one will be positive, and this we can say that these 2 will be same sign, that is positive. So now what will be the sign of these 2? This will be a negative sign, isn't it? Then we will get the node here. So these 2 will be negative. And considering the next one, that is the fourth molecular orbital, here we have 3 nodes, isn't it? And the first one will be always positive, and here it is the fourth one. So one is first one is the last of the all of this will be in an alternative manner. So the first one will be positive, then this one, second one will be negative, third one will be positive, and the fourth one will be negative, isn't it? So this will be a negative one, and we have to introduce 3 nodes, isn't it? 3 nodes here. So how can we implement these 3 nodes? So here we can use a trick, that is the middle one will get a node, then the first and last one will get a node. So now we check this. The first one will be positive, so here is a node we introduced. Then what will be this sign? This will be negative, and this will be also negative. Then here we will not have a node, so this will be negative. And we have a node here, so what will be the sign of this? This will be positive. And here we will not have any node, so we will have a positive sign here. So this will match, that is here will be a node can be introduced. So we fill the fourth one also. And next we will get into the fifth molecular orbital. Here we have 4 nodes here. So the first one will be positive, and the last one will be, what will be the last one? This is positive, this is negative, then this will be positive sign. So here we have to introduce 4 nodes in this. So I introduced this 4 one here like this. First one, second one, last one, and here I introduced node here, and we'll put the signs according to these nodes. So if it is a positive one and here is a node, then what will be this one? This will be negative. And if it is negative and here is a node, what will be the next one? This will be a positive. And here is no node, then what will be this one? This one will be also positive. And if it is positive and here is a node, then what will be this? This will be a negative. And this matches with this, isn't it? Here is a node and this is negative and this is positive. And I already said that in the C4 system, this will be in an alternate manner, because all this will have to be introduced by a node. Then will be the number of node will be correct match with the nodes. So this will be positive, negative, positive, negative, positive, and negative. And this is the C6 system. And now we have to introduce the electrons to this. So in the ground state, the electrons, if this is a C6 system, so the electrons will be 6, isn't it? Yes. So we have to introduce 2 electrons in one molecular orbital, isn't it? So the first molecular orbital will have 2 electrons, and the second one will be 2 electrons, and the third one will be 2 electrons. And we introduce all the electrons, 6 electrons to the system. This is the ground state. And here what will be the HOMO? The HOMO will be the third one, isn't it? This is the highest occupied molecular orbital. So the HOMO will be the third one, and the LUMO will be the fourth one. And if we consider the excited state, the first one will have 2 electrons, second one will have 2 electrons. The third one, 1 electron will be excited to the fourth one. So the third one will have only 1 electron, the other one will be excited to the fourth one. So here the fourth one will be the HOMO, highest occupied molecular electron orbital. Then the LUMO will be the fifth one, isn't it? Here we will have any electron, so LUMO will be the fifth one. This is the C6 system. Now we will consider the C3 system. C3 system is an allyl system, that is CH2 double bond CH2. And now we draw the molecular orbitals of allyl system. First draw one line, that is the energy line, and then draw 3 lines like this. Then it is a C3 system, so I draw 3 orbitals like this, and then we have to put the signs for this. For putting the sign, we have to know the nodes. So the first one will have 0 nodes, second one will have 1 node, and the third one will have 2 nodes. So the first one will definitely be positive sign upper part. So this will be always positive in all this part, and the second one will have positive sign in the first part and the negative sign in the last one, and it has a one bond. So how we draw this will be different from the C4 and C6 system. Here this part we will not draw this one. Instead of this bond we will draw a dot here, and this is considered as the node. So here only two molecular orbital will be here, and this one will be considered as the node. So we have to draw a dot here, and this will be the node. And in the next one, the third one, we know that this will have alternate signs, that is here positive, negative and positive, and all this will have nodes. So the two nodes here, and now we have to put electrons to it. It is an allylic system, so the electrons can be introduced by three manner, that is allyl cation. Cation will be have a positive sign here, so it will have only two electrons, that is because it is a cation, it have only two electrons. So the two electrons can be introduced to the first state, that is the first one. So this will be the HOMO. We only have two electrons, so this will be the HOMO, and the next second level will be the LUMO. For what? For the cation, allylic cation. And next we consider allyl radical, that is it has three electrons for allylic radicals. This is the allylic radical. So how can we introduce three electrons? First we will introduce two electrons here, and then the second level will have only one electron. So the highest occupied will be the second one. This is the HOMO, and this will be the LUMO. And for the allyl anion, anion will have more electron, isn't it? So it has more electrons, so it has a 4 electrons in it. So the first two electrons introduced to the first level, and the second level will have 2 electrons. So this will be the HOMO, and the third one will be the LUMO. Now we consider the pentadiene system, that is C5 system. For C5 system, CH2 double bond, CH single bond, CH2 double bond, CH single bond, CH2 will be the C5 pentadienyl system. So in the energy diagram we will have to put 5 lines here and introduce how many will be, this will be 5, isn't it? We will introduce 5 here, and then we will introduce 5 orbitals to the last one, and that is the upper one. Here it is it have a change, that is like the third one, the C3 system we draw one as the point. So here we also introduce this point to many systems, many orbitals. So we will consider first nodes here. The nodes, the first one will have 0 nodes, so we draw 5 orbitals. The second one will have 1, then 2, then 3, then 4. So the first one will all have positive signs here. Then the second one will have 1 node. So the I introduce the node in the center, and both the sides have 2 orbitals, and this will be positive, and here is a node, and this 2 will be negative. Then we will go to the next third one. Here it has 2 nodes here, so I draw first one, then the second one, instead of drawing the second one I draw a dot here. This will be the node, so there will not be the second one present here. Then I draw the third one, then next I draw the another node here instead of the fourth one, and next I draw the fifth one here and put the positive sign for the first one, and here what will be the sign? Here will be negative signs because it has a node here, so this can be two positive signs. So this will be positive, then this negative, then this will be positive. And the next level have 3 nodes, isn't it? So like the first one, I draw the middle one as the node. Then if I draw three nodes and did not draw the orbitals, then only 2 orbitals will be left. That cannot be considered. So what can we do now? So we can do that. The first one will first 2 one will be draw here, and the second 2 one will be draw here, and we introduce a node here like this, because it has a positive and this has a negative sign, and this will be a positive and this will be a negative. This is how we draw the C5 system. And what will be this? We already know that the first one, that is the upper one, will be always have an alternate sign, that is positive, negative, positive, negative, positive, isn't it? So we have drawn the signs for the C5 system, isn't it? So next we have to draw the electrons. We know that this is a C5 system and we have 5 electrons with us, but for cations, as it is an allylic system, C5 is an allyl system, the cation will have only 4 electrons, isn't it? So the first 2 electrons in the first one and the second 2 electrons, the left 2 electrons will be the in the second one. So this will be the HOMO, and the upper one, third one will be the LUMO, isn't it? In the radical we have 5 electrons, isn't it? So first 2 is here, then 3 and 4 will be here, and the fifth one will be in the third molecular orbital. This will be the what will HOMO, and this will be the LUMO. And for anion, here it will have 6 electrons for anion. So the first 2 is here, 3 and 4 here, 5 and 6 is here. This will be the HOMO. This will be the HOMO, and the upper one will be the LUMO. So we have drawn C4 system, C6 system first. That will be a simple one, isn't it? Then we draw the C3 system and C5 system. C5 system. This is a little bit difficult because of these nodes, isn't it? Just remember these nodes, how it drawn, then it will be a simple one. So this is how we should draw the molecular orbitals for these systems. Next we will talk about the next topic, that is the pericyclic reactions of 3 types, that is electrocyclic, cycloaddition and sigmatropic. This will be uploaded in the next video, so stay tuned. Bye.